square root of 2. That will be the square root of sigma 1 minus sigma 2 squared. Okay. So because you don't have the actual numerical, well, sigma 3 is equal to 0, so that's not a problem. So just using that 0. Because you don't have any excess or you don't have the complete numerical value, then of course your unknown here will be that thickness T. Yes? So your sigma 1 is equal to PR all over that thickness, pressure and radius, known, unknown is thickness. So let's have this one as 5 megapascal, and then you have this one to be 0.5 of a meter, so megapascal meter thickness, right? And then you have your sigma 2 to be PR all over 2T. That's 5 megapascal, so let me remove the unit. 0.5 all over twice the thickness. Okay? So this is known. All other parameters are known. You just have one unknown. One equation, one unknown. You should be able to solve that, yeah? So what's the thickness? Anybody?
Sure.
So it seems you're not familiar to this kind of problems. Yeah. Anybody who would like to try? So you put everything there, take the square root or take the square of both sides, that makes it simple. How about we try that? So if I'm going to expand this solution, 250 divided by 4, what is that value? Divided by 4. 165, 66.5, yes? So I'm just going to check the units. So what I'm going to do is to check my units. 250 will be in megapascal. That will be in megapascal. And I have this one to be 1 over square root of 2. So what do I have here? Um, 2.5, yes? So just checking. I'm just going to start first with putting in my units. Megapascal meter divided by that thickness. That will be squared. Then you have this one to be a plus. What do we have? Sigma 2 squared. This one is okay, 2.5 minus 1.25, yes? So this one is 1.25. So this one is 1.25. And this one will be 2.5. Is that okay? So what do we have? We have now 62.5 megapascal. So I'm just putting in the units just to check that my my final unit will be correct. And then I have this one to be, what's this one? So that will be 5 megapascal meter. Is that okay? So what happens now? So anyway, that's square root, so it will be the same. I'll multiply this one with square root of 2. And then I have this one to be 5 megapascal meter thickness. And then I bring there my thickness. That will now be 5 megapascal meter. Square root of 2, 62.5 megapascal. Cancel out megapascal. I have now my thickness in. Okay. So what do we have?
What do you get? 2.056.
Okay, so what do we have?
This meter. There's 2 liter too much, so we already exceed the criteria.
So just stick lah.
Yeah, just stick.
So please check if my solution is correct. Please look at the steps. But this will be basically the procedure wherein you equate your working or design stress or design strength, to the stress that you needed. So in this case, we're equating this yield divided by a safety factor, equating it to the bond stress. Okay, and then from here you can get your thickness. Chances are since this one is a very general problem, in reality, the safety factor for the principal stress is higher than the safety factor for the von Mises stress criteria. So what do you get here? So let's try to consider that we have safety factor to be the same for the principal stress criteria and the von Mises stress criteria. What's the thickness here?
57 mm.
Sorry? 0.0566. Yes? So this will be what? 56.6 millimeters. So this one is a more conservative design than the principal stress criteria. Of course, another criteria is of course looking into the fracture mechanics criteria, wherein you assume a size of a crack and then determine the thickness of your pressure vessel. So we have different design criteria. First, you look at the failure criteria. What is your failure? Is it fracture? Is it principles? Is it breaking, principal stress? Is it yielding, bond pieces? So identify your criteria, and then from there you can determine your design or determine the different geometry of your design. Okay, so in this case, we have a thickness of 56.6 mm. So again, depends on which one you want to use. But this bond pieces yield criteria is more conservative than the principal stress criteria. Okay, just to give you an idea, what are problems being given in pressure vessels? It's all the same. If you try to look at your notes, it's all the same. It's just looking at the comparison between thick and thin walled pressure vessels. If values are not given, I think the solution is very straightforward. I think similar to what we have discussed. So you should know all these parameters. You should know how to use them. Okay, so that's just the thing for pressure vessels. For the derivation, if you're interested, I can pass you my materials. Let's have a look at this one. Just it's not about pressure vessels, but it's about combined loading. Have a look for this one.
Wow, so long.
Solve for your normal stresses and solve for your normal stress and shear stress and determine the diameter of your shaft. By the way, can I ask you, since all of you are having a mechanical engineering background, if you have stress equal to My over I, this one is stress due to bending, what will be this y? My over I. If you have a cylinder, if you have a solid shaft, circular shaft, My over I, what will be that y? Radius. So you have this one to be your. What about torsion? Shear stress. DC over J. So you have, what is C? You know the different types of loading conditions, right? Bending, tension, compression, torsion. So your shear stress will be DC all over J. What is C? Circular solid shaft. Still the radius. Okay, so please solve this one and let's solve it later. Okay, try to solve this one. Solve for the shaft diameter, combined loading, nothing new from this one. Solve for sigma 1, solve for sigma 1, 2. Sigma 2, 2 is, sigma 1, 1 is this one is your shear. Sigma 1, 2, and sigma 2, 2 is your. So as you can see, you have a factor of safety here. You have your tensile strength there.